Welcome to Complex Analysis. This is a series of lectures on the main results on holomorphic functions, session number 4. Today I ended the last session, which was on maximum modulus principle, with a question: how will I formulate analogous minimum modulus principle? I gave also an example. Okay. Today we will again look at that example, try to see how to formulate, and try to give some applications of minimum modulus principle. So the example we looked at was the following. My open set is the open ball B01 in C, and the function was from U to C, the identity function f of z equal to z, right? Then we know that if I look at mod f, okay, this is less than or equal to mod z, which is less than or equal to 1, and f of 0 is 0, right? Therefore the minimum is attained at 0, yeah, which is an interior point, which is a point of the domain, the open set. So how do you think I should formulate? If you think carefully, you will arrive at this. As usual, there are very equivalent versions. I will try to formulate it the way we formulated the maximum modulus principle. So let U be open and connected. Did I share my screen? Yes. Open and connected. And let F be U to C be holomorphic. Okay. Assume Z0 in U is such that modulus f of Z0 is less than or equal to modulus f of z for all z in U, or for all z in some b z0 of R. So local minimum. Okay. So Z0 is a local minimum for the function mod f. Then what do you think should happen? Let us look at the earlier case. So we have to rule out f of Z0 is 0. Therefore either f of Z0 is 0 or okay, f is a constant. If it is not 0, then it must be constant on U, of course. But notice that Z0 is only a point of local minimum for mod f on a small open ball. That's enough. I don't want it to be global minimum on all of U. Okay. Proof is essentially one line. So if f of Z0 is 0, there is nothing to prove, right? Therefore let me assume, okay, f of this is okay, assume this, right? Therefore what do I have? So on B Z0 of R, right, since mod f of Z0 is less than or equal to mod fz, okay, this is already positive. It shows that f does not vanish on only the open ball B Z0 of R. Okay, it may vanish elsewhere, I don't care. Okay, then what do you think you should do? I'm sure all of you know the moment it does not vanish on a set, what do you think you'll be tempted? And also remember, you want to apply maximum modulus principle, right? So the obvious, right? What should I do? Define g of z to be 1 by f of z. For what z? For z only in B z, not apart. Right? So what does this mean? Since mod fz is greater than or equal to mod f of z0 for such z, then what do I have is mod gz is less than or equal to 1 by mod f of z0. Right? You understand that? Yeah? And z0 is a point of this open ball. Therefore, that means z0 is a point of local maximum for mod g on the open set B z0 of R. Right? Therefore, by maximum modulus principle, principle, G is a constant where on its domain, the domain is only B z of R, right? That means F is a constant. Again on where? On B z of R. Be careful, right? Now I can use uniqueness theorem. What does uniqueness theorem say? If a set, if a holomorphic function vanishes on an open set, it should vanish identically on the connected open set, right? Since U is connected by uniqueness theorem, if you want to say it's a constant, let's look at the function constant f minus c. Then this is 0 on B z naught of R. Okay, and this is an open connected set. Therefore, by uniqueness theorem, f is a constant on U. Okay, make sure the proof is extremely simple. Pause, review, proceed. The only thing you have to be careful is we are applying maximum modulus principle to G because the domain is only open ball. Okay, therefore I know I can conclude only G is constant on that open ball. That would mean F is a constant because G is 1 upon F, therefore F is also a constant on P z naught of R. Okay, but then now I have to use uniqueness theorem again. Okay, understand this proof. Okay, so as an application, I shall put two results. Okay, one is again, suppose you have, okay, application 1. Okay, let f of z be a non-constant polynomial. Okay, then there exists an alpha and c, so that f of alpha is 0. This is the most crucial part of fundamental theorem of algebra, right? Once I find one root by induction, I can find there exists n roots. Okay, that I do not go into. You can try look into my book. We had already seen two proofs. Do you remember where we have seen two proofs? Yeah, one is by using Cauchy's theorem, which except my book I don't find any other book, and second is the standard thing, Liouville's theorem. This is the third proof, right? But remember, all the proofs will use a very crucial fact about polynomials. What is the fact? The fact is, okay, mod f of z goes to infinity as mod z goes to infinity. What does that mean? That is, for every m positive, there is an r positive, so that for every z, so that mod z is less than r, mod of f of z is greater than m. This is what is the meaning of this. If you have learned my analysis course, and you especially the video on limits, you would have learned these things very well. Okay, because many students have very vague idea about what does it mean to say mod f z goes to infinity as z goes to infinity. This is the definition. So this means something like this. If you give me an m, okay, let us say m, okay, this is m. Okay, now I just have to find one r, so that after this, take any point, it's a mod f z, okay, that will be greater than this m. This is my m, this is my 0, mod f z will be lying here. Okay, keep this pictorial thing in mind. Right, that fact I am going to use. Right, now first assume that if a0 is 0, okay, the result is easy, because then f of z will be a1z plus a(n)z power n, and therefore z times I can write a1 plus a(n)z power n minus 1. Therefore, or I can take alpha to be 0. Okay, f of 0 is 0. Therefore, let me assume a0 is not 0. Okay, understand this? Right, now since I know f of z goes to infinity, okay, so take m equal to 2 times mod a0. Okay, then there is an r greater than 0, so that whenever mod z is greater than or equal to r, modulus fz is greater than or equal to 2 times mod a naught. Right? Okay. Now let us look at the compact set B0R. Right? Now let me restrict my f to this compact set B0R. Then this is continuous. And hence mod f is continuous. On everywhere, in particular on this. Right? This is a continuous real valued function on this compact set. So what do I know? It has a minimum. Okay, therefore mod f has a minimum. Right? Okay. Now let's look at minimum modulus principle. What does it say? If some point is a minimum, okay, if some point z0 in B0R is said that mod f z0 is a minimum for all z, okay, right? So if you want to make it 2r, just for fun, okay, you will see why I am looking at 2r, okay, 2r in B0 2r, okay. Then what do I know? F of z0 must be 0, right? So how am I going to prove that? Very easy idea. So see, if it is not attained in the interior, since the compact set, then where should it attain? It should attain on the boundary, right? Let us look at what happens on the boundary. What is the boundary? Boundary is mod z equal to 2r, which is greater than r. Therefore, modulus of f of z for on the boundary is greater than r equal to 2 times mod a naught. Right? But let's look at, therefore, for everything on the boundary, this is my 2r. Okay. So for every point here, the modulus is greater than or equal to a naught. But what is f of 0? F of 0 is a naught, and hence modulus is a naught, which is less than every point, okay, every value here on the boundary. You understand? Please understand this carefully. So I know it has to attain a minimum. Mod f must attain a minimum on this closed and bounded set. Okay. But on the boundary, it's always greater than or equal to 2 mod a naught. But at the interior, it is less than that. So what does it mean? And therefore, there exists a z0 in BA2R so that f of z0 is 0. Because if it has to attain a point z0, this point z0 cannot be on the boundary. Right? Therefore, it has to be in the interior. Okay? But once it is in the interior, then we know minimum modulus principle says then f of z0 must be 0. There is no way out. Okay? Please understand this logic carefully. Second application is a theorem which is called open mapping theorem. I plan to produce another video completely on open mapping theorems because there are many open mapping theorems in various parts of analysis. Okay, they are all very important, and there is a very unified way of looking at what they really want to say. Okay, and people get worked up with the proof and try to understand it in isolation, but there is a unifying principle why all of them are there, what do they want to say, what is their significance, is there any kind of common thread? That I will explain later. Today we will stick to this problem. What does it want to say? Suppose I have a function f which is holomorphic and non-constant. And as usual, u is connected and open. then F is an open map. So what does that mean? That is, if V contained in U is open, then F of V is open. Okay. So let us go through the proof. The proof is again very geometric. It uses only the minimum modulus principle, and in fact the trick is just now we used it in the fundamental theorem of algebra. The same trick is what I am going to use. Okay. So these two applications will tell you how to make a deft use of the minimum modulus principle. So how do I do that? Okay. So let V be open. Fix an A here. Therefore there is an R such that BA, let me say even the, okay, some to R, okay, this is contained in V, right? Okay. Now what do I want? So right, maybe I can even this. Okay. Now let's look at BAR 0 less than R less than capital R, right? Now I have to say this F of B A capital R, okay, this contains F of A. Therefore I have to say there exists an epsilon positive such that B F of A epsilon is contained in F of B A. That means F of A is an interior point of this domain, but this is contained in F of V, right? Therefore, given any A in V, F of A has an open ball centered at that point which is contained in F of V. That means F of V will be open. Do you understand this? Okay. This will show F of V is open. Okay. Please understand, this is all I have to prove, right? So how do I plan to do that? The first thing is, again we are going to use uniqueness theorem. Let us look at F of A, right? Then do you remember, let us just, after uniqueness theorem I made an observation, okay, an observation following that. What is the observation? Suppose F is holomorphic from U to C, okay, if you want to assume connected etc, okay, and suppose A is there, okay, A is any point in U and lambda is any complex number, then I said, okay, there exists an R positive such that, okay, F of Z is not equal to lambda for Z in B A R and Z not equal to A, right? So you may remember I said if lambda F of A is not equal to lambda, then by mere continuity of F will prove this. I can find anything. So the important thing is, if FA equal to lambda, then I can still avoid. Okay, please remember, many of you may not have appreciated this result when I proved it. Okay, this is a very beautiful result which is not true, because now I have functions which are completely zero on this. Okay, a C infinity function which is zero. Okay, so I can have function which I identically vanish on an open set. Okay, C infinity function in real analysis, I can't do that. Please understand. Okay, now therefore there is an R positive so that, okay, maybe make it rho positive so that, okay, for every Z in B A rho and Z not equal to A, F of Z is not equal to F of A. That is my lambda. Okay, F of A is not equal to, sorry, see, yeah, by this theorem I can choose that. Okay, now choose any row, okay, so that the open ball B0R, this is contained in B0 BAR and BA row, and which is contained in BAR, which is contained in V, and so on. Okay, right. Is it clear? Okay, so let us have a picture. So this is my u, maybe make it a v. This is my a, I have a bar. Okay, now I have, this is my bar. Okay, let cr equal to z, so that mod z minus a equal to r. Okay, now this is the circle centered at a with radius r, therefore we know this is compact, right? Yeah, now for any z in cr, f of z is not equal to f of a. Why? And for any z in ba rho, f of z is not equal to f of a, and the closed ball bar is contained in ba rho, therefore for any z on the circle also it is true. Okay, now this is a compact z, therefore the function z going to mod fz minus fa, this is continuous and it's always positive, and therefore it attains a minimum, right? Right, so let's say z0 is a minimum, that means mod fz minus fa is greater than or equal to mod fz0 minus fa. Where does z0? Z0 is in cr, therefore that is positive. Okay, so call this as 2 epsilon. Let 2 epsilon equal to minimum of f of z minus f of a modulus as z varies over cr. Right, now what do you think I want to prove? So again have a look at a picture. This is my f of cr and this is my f of a, right? So what the minimum distance is at least 2 epsilon. You understand this? Yeah, whatever distance you take, this will be greater than or equal to 2 epsilon. So what do you think since I chose 2 epsilon, I'm sure what you know what you want to say, right? What do you want to say? You want to say, look at the open ball with this epsilon. Okay, so we would like to claim b fa of epsilon is contained in f of b a r. In fact, I would like to claim it is contained in f of b a r. Okay, this, I hope this is what I want to prove, because I know, right? Is this clear? Yeah, then I would have been through. Now how do I do that? This is where we want to use a minimum modulus principle. So if I want to show this is contained in this, what do you think I should do? Start with any w in b fa epsilon, then I want to say there exists x z in bar such that f of z equal to w. This is what we want to do, that is we want to prove this, right? Yeah, so I want to use minimum modulus principle. As you can see, minimum modulus principle isolates 0, right? So I have to find a function, so I want to find a z such that fz equal to w, but I also want to use minimum modulus principle. Then what do you think I should consider? Consider the function g of z equal to f of z minus w on b ar. Okay, so this is continuous on this and holomorphic on bar, right? So since this is continuous, mod gz must have a minimum. On the compact set bar. Okay, if I say the minimum is has to be attained at in the open ball, then by minimum modulus principle it must be 0. Do you agree? Please listen, this is exactly the same thing. Again, I would like you, after watching this video, compare the proof of fundamental theorem of algebra and this open mapping theorem. You will see the argument is exactly the same. So what I am going to show, okay, I am going to show g of z. Okay, I want to show what is its value at on CR. Okay, I want to show what is its value. It is greater than or equal to something, whereas g at a, what is g at a? G at a is f of a minus w, but where does w? W is in b f a epsilon, therefore this will be less than epsilon. Therefore if I show this is greater than or equal to epsilon, I am through. I am going back and forth. You see that? Yeah, please don't be intimidated. Okay, line by line proof anybody can give, but this is the way we want to. We know this. Therefore if I show, look at the fundamental theorem of algebra, that's what we also did. This is my 0 to r, and I said here it is greater than or equal to mod 2a naught. Okay, at this point it's mod a naught, therefore the minimum is at an interior. You see that? The same trick is what I am using here. Enjoy mathematics. Okay, let us look at what is g of w. G of w is f of g of z is f of z minus w, right? Okay, right. Now let us try to estimate. What do I know? W is in where is it? Yeah, b f epsilon, right? Okay, therefore what I know is if I take any point, where is let me go back. Yeah, for z and cr, right? Yeah, so f of a minus w, because w is in cr, sorry, f of a, uh, let me just correct my thoughts, I got lost somewhere. Okay, yeah, f of a minus f of, I want a point on the boundary, therefore yeah, z, for z in, oh right, I'm sorry, oh yeah, I got it. Okay, f of z, okay, this is what I am looking at. Okay, this is less than or equal to f of a minus w plus w minus f of z, right? F of a minus w, okay, therefore f of z minus w, which is mod gz, is greater than or equal to f of a minus f of z plus minus f of a minus w, right? Now remember, where is z? Z is in on the circle CR. Okay, yeah, so yeah, right. So I'm sorry, this is the cause of my problem. I want to show for z in CR mod gz is greater than or equal to epsilon. I was mentally I was working in BAR, that's why I got confused. Please understand, my z is in CR now, right? If z is in CR, then I know fa minus fz. Okay, this is always greater than or equal to epsilon. But remember, w is in the epsilon distance, therefore this will be greater than or equal to minus epsilon. Fa minus w is less than epsilon, therefore minus of that will be greater than or equal to epsilon, therefore this is epsilon. Therefore what I have shown, for z in CR, I said modulus of gz is greater than or equal to epsilon, but at a, which is in the BAR, mod g of a is f of a minus w, that is less than epsilon, right? But since mod g must have a minimum on the closed and bounded disk, which is a compact set, okay, and the minimum cannot be attained on the boundary, therefore must attain a minimum inside BAR. Okay, but what does that mean? So by minimum modulus principle, then let us say z0 is a point in BAR, then mod g z0 must be 0. That is same as saying f of z0 equal to w. So we proved f of b of f of a epsilon is contained in f of BAR, which is contained in f of BAR, etc., etc. Therefore, FA is an interior point of this, and A was arbitrary, therefore this is open. Okay, pause, review, proceed. You see that this always happens. Okay, just now I said the proofs are similar, the fundamental theorem of calculus and here open mapping theorem. I was very sure, I just now proved it without any hitch. When it came here, momentarily lost my thing, right? Thinking was lost for a few seconds. So when I wanted to say mod gz is greater than or equal to epsilon, I said z must be on the boundary, but while working I took z to be in BR and got little confused. So it happens always. You should not be discouraged by that. Okay, right. Just to say, okay, this happens to all, so don't worry. Okay, come back. Now there is a third application to minimum modulus principle, that is maximum modulus principle. Sorry, sorry. Open mapping theorem implies maximum modulus principle. Okay, but this is a somewhat vicious circle. See, I used maximum modulus principle to prove minimum modulus principle, and I shared the screen. Yeah, I used minimum modulus principle to to prove open mapping theorem. Now I am going to prove open mapping theorem implies maximum modulus principle, right? But later in the course we will give a direct proof of open mapping theorem. Therefore, it will follow. Okay, well, maximum modulus principle implies open mapping theorem, and open mapping theorem implies maximum modulus principle. Therefore, they are logically equivalent statements. Okay, in fact, for modern people who are a lot more topology in our blood, open mapping theorem actually explains the maximum modulus principle. Okay, even though possibly maximum modulus principle was found out earlier, but in modern sense, open mapping theorem is the one which really explains why maximum modulus principle is true. Okay, anyway, I will come to that when I said I have a video in mind in which I will talk about open mapping theorems and analysis. I will explain this there. Okay, at present let us do that. Okay, so let this be holomorphic, and as usual this is open and connected. Okay, right. Now what I am going to claim is very simple. Let z, or let us say a be any point in U, right, and assume f is non-constant, holomorphic and non-constant. Then give me any u for every u in U. Do you remember I said when I stated open, sorry, maximum modulus principle, I said equivalently you give me any z in the domain U, then I can always find another z dash such that mod f z dash is strictly greater than mod f z if f is non-constant. Do you remember that? That's what we are going to prove. Given any there exists z in U such that mod f z is greater than mod f u. Do you follow that? But this is utterly trivial. Think geometrically. So I have fa. F is non-constant, right? And f of u will be some open. Okay, f of u, this is open because by open mapping theorem f of u is open. This is my fa. right? Therefore, what do I know? I know there exists an open ball around this. Okay, there is an R positive, so that B F A R is contained in F of U, right? Now let's look at, so F of A plus R by 2. Okay, so this belongs to B F A R, right? Yeah. So are you following? Right. Oh, but this may not. Let's say just, I'm sorry. I'll just modify this proof. This FA is this. Therefore, I should go in this direction. Right? Okay. Suppose if FA is 0. Okay. If FA is 0, then I can always take R by 2. Okay. That will be in B0R. Right? And this B0R is contained in F of U. That means there exists Z in U, so that F of Z is equal to R by 2. Therefore, therefore mod Fz is greater than mod F0, F of A. Are you following? So let us assume, so understand this. So let me assume F of A is non-zero, right? Okay. Now let us write F of A equal to R e power it. Therefore R is positive, right? And not this R, so I'm sorry. Let us say R e power it, right? Now consider R plus R by 2 e power it. This belongs to B of F of A R. Yeah, because what is the distance? So consider this as a W. W minus F of A will be this R e power it, R e power t, therefore R by 2 e power it modulus, therefore R by 2, which is less than R, right? Therefore this belongs to, see that now the picture showed, it's exactly the same direction angle. I just have to push it. Okay. Now do you believe geometry helps me? Whereas my earlier thing was slightly wrong. Okay, good. Okay. Therefore R plus R by 2 e power it belong to B of F of A R, but that is contained in F of U. That means what? There is a Z in U, so that F of Z equal to R plus R by 2 e power it. Yeah, but mod F of Z is R plus R by 2, which is strictly greater than R. Yeah, so we proved the result what we wanted to show. If F is non-constant, okay, right, I can find this. Let me ask you a question. Where did I use the fact F is non-constant? Yeah, because I wanted to use open mapping theorem. Open mapping theorem said if F is non-constant and U is open and closed, sorry, U is open and connected, then F of U is open. Go back. Let me see. I made the statement correctly. Yeah. Look at this. So that is the only place where used non-constant. After that, everything follows. Yeah. Okay. So I hope you enjoyed this lecture. You can also see I have some vague idea and I depend upon my geometric intuition to arrive at a correct proof. Okay. So you don't have to read and line by line check and memorize the proof. Oh, okay. But of course in an exam, memory helps to write the faster thing, right? In 3 hours you have to write the exam, you have to learn. But do this, you will see that it's much easier. Okay. You won't be afraid of exams because you can quickly come up with a thing. Okay, I hope you enjoyed. We will meet again. Take care and stay safe.